In previous lessons, we saw that limits arise when finding the instantaneous rate of change of a function or when trying to find the tangent to a curve. In this lesson, we will give the informal definition of a limit of a function. Then we will see how to calculate the value of these limits. Let's begin with an example. Consider the function f of x equal to x squared minus 1 divided by x minus 1. Frequently in calculus, we're interested in studying the behavior of a function near a point but not at a point. So for this function, you can notice that if you plug in 1 for x, you'll be dividing by 0. So this function is not defined at x equals 1. But we can still try to investigate the question, how does this function behave near x equals 1? Let's first look at the graph of this function. So the graph of f has a little hole at x equals 1, and the graph of f actually looks like a straight line except for that hole at x equals 1. And we'll see why in a second. So consider the rational expression x squared minus 1 over x minus 1. If you look at the numerator, this is the difference of squares, x squared minus 1 squared. So it can be factored as x plus 1 times x minus 1. So f of x can actually be written in a factored form as x plus 1 times x minus 1 divided by x minus 1. And if you notice that if you plug in any value of x into this function other than 1, that the terms x minus 1 will just cancel out in the numerator and denominator. So for x not equal to 1, f of x just simply reduces to the expression x plus 1. So that's why the graph of this function f looks like a straight line, because the function f of x acts like the function y equals x plus 1 for any value of x other than 1. So the function f of x can actually be simplified to just equal x plus 1 for any value of x other than 1. So the graph of f of x on the left looks very much like the graph of the line y equals x plus 1. So we're trying to investigate what is the behavior of f as x gets really close to 1. If you see the graph on the left, there's a little hole in the graph of f of x. But what is the height of this hole? It appears the hole is at height 2. And if you compare the graph of y equals x plus 1, we see that on this graph actually passes to the point 1, 2. So the hole in the graph of f of x is at the height 2, and so it appears that the value of f of x is getting closer and closer to height 2 as x gets closer and closer to the value 1. So if you take a value of x very close to 1, the function's values are getting very, very close to 2. So this leads to our definition of a limit. We see that the values of f of x get very, very close to 2 as x gets really, really close to 1, even though the function isn't even defined at x equals 1. So now let's give our informal definition of a limit of a function. We say the limit of f of x as x approaches a equals the number L, and we write this notation: if the values of f of x get arbitrarily close to L as the values of x get sufficiently close to a but not equal to a. So let's think about this definition. If you look at the graph of a function, the y-coordinates of points on the graph are the function's values, f of x. So we're saying that if you're looking at a graph, when the x-coordinates get closer and closer to a, some value a, if the y-coordinates, the function's values, get closer and closer to some number L, then we say the limit of f of x as x approaches a equals L. So consider our first example function, f of x equals x squared minus 1 over x minus 1. We saw that as x gets closer and closer to 1, the function actually gets closer and closer to the value 2. So with this new notation, we could write the limit of f of x as x approaches 1 equals 2. Or you could write this with the definition of the function as the limit of x squared minus 1 over x minus 1 as x approaches 1 equals 2. So we're saying that the value of this function, x squared minus 1 over x minus 1, these values get closer and closer to 2 as x gets closer and closer to 1, but not equal to 1. Remember, this function isn't even defined at x equals 1. As x approaches a, we're not concerned with the function's value at a. We're just concerned with what is happening as the function approaches a from both sides. Let's consider another function called the identity function. So let's define g of x equal to x. So no matter what number you plug in for x, the function's value also equals x. So consider the limit of this function. Let's look at the limit of this function, g of x, as x approaches a. Well, the definition of g of x is just x. So think about the definition of limits. We're trying to figure out what value does x approach, what number is x getting closer and closer to, that is the y-coordinate x here. What value is this x approaching as x gets closer and closer to a? Well, clearly, as x gets closer and closer to a, x will get closer and closer to a. So the answer to this, if this was a limit question, this would have to equal the number a, no matter what a is. For any real number a, the limit of x as x approaches a would have to equal a. So I can substitute any number in for a that I'd like. So for example, what is the limit of g of x as x approaches 5? Well, as x approaches 5, the limit of x will be 5. How about an even easier function, like the function defined by a constant? F of x equals a constant c. So this is a constant function. Whatever value you plug in for x, the f of x value will always equal c. Let's consider the limit of f of x as x approaches a. Well, f of x just equals the constant c for any value of x. So as x gets closer and closer to a, the number c is not going to be affected by your choice of x or whatever x is doing. So the limit of c as x approaches a will just equal c. The value of c is always getting closer. It's staying the same. It's always equal to c no matter what happens to x. So for a more concrete example, consider the function g of x defined as g of x equals pi. So pi is a constant. It's about 3.14. So let's look at the limit as x approaches 7 of g of x. Well, g of x just equals pi for any value of x. So as x gets closer and closer to 7, pi is getting closer and closer to pi. It's just equal to pi for any value of x. So this limit would just equal pi. Now let's consider a couple of special cases where the limit as x approaches a, actually you can't given answer. We would say the limit does not exist. So consider the piecewise defined function f of x, which is going to equal -1 if I plug in x less than 0. And if I plug in a non-negative value for x, then the function f of x will equal 1. So this function only takes on two values. So let's look at the graph real quick. Here's a rough sketch of the graph. It only takes on two values, -1 and +1. So for any value of x less than 0, the function's height will be -1. So this function will be a flat line. So the graph to the left of the y-axis will look like this. And then to the right of the y-axis, we'll start at height 1 and continue to the right. So this is a rough sketch of f of x. So let's consider the limit of this function as x approaches 0. So what value is the function approaching as x approaches 0? Well, if you follow this function, let's say from the left, so we're getting closer and closer to x equals 0. That's right on the y-axis. As we go along the function that starts near x equals 0 on the left side, so as we follow along this curve from the left, the value of this function is getting closer and closer to -1. But if you follow the function on the right side of the y-axis, then the function is getting closer and closer to height +1. It actually always equals +1 on the right, and it always equals -1 on the left. So it appears that we have two possible answers here. As x gets closer and closer to 0, well, the function could be getting, we could say the limit is 1, or we could say the limit is -1. But for the definition of a limit, it doesn't say which side to approach 0. You have to consider both directions. Since the limit from the left is -1 and the limit as x approaches 0 from the right is +1, we can't say that this function has a limit. So in this case, we say this limit does not exist. So it can happen that the limit of a function as x approaches a number does not exist. And here's an example of how that could happen. If the values on the left side and the right side there's a big jump between the two values, then the limit does not exist. And often we just write DNE for does not exist. Here's another example of a function with a limit that does not exist. Consider the function g of x equals 1 over x squared. So this function is not defined at x equals 0. In the graph of this function, it looks like it has a vertical asymptote at x equals 0. So at x equals 0, the function goes straight up. From both sides, the function goes straight up. The values get arbitrarily large as x gets closer and closer to 0. So consider the limit of g of x as x approaches 0. Well, if you can see from the graph, the values of g of x are getting larger and larger as x gets closer and closer to 0. But these values are not stopping anywhere. You could find a value of g of x as large as you want by taking a value of x closer and closer to 0. So this limit does not exist either because the values of g are not approaching one single number as x gets closer and closer to 0. Because the values of g of x are getting infinitely large as x approaches 0. So even though we say this limit does not exist, we'll talk about this in future lessons about infinite limits. Even though the limit does not exist, we can often write, in this case, that the limit is infinity because the graph is getting the values of g are getting infinitely large. But infinity is not a number, so officially the limit does not exist, but to indicate that it's not existing in a special way, sometimes we would say the limit is infinity. Let's look at one more special case when a limit does not exist. Consider the function f of x equals sine of 1 over x. So since x is in the denominator, we see that there's going to be a problem with this function as x gets closer and closer to 0. So again, we're going to look at the limit of f of x as x approaches 0. Now the graph of this function, since this is a sine function, it's kind of like a wave, and the regular sine function has a nice wave pattern. It repeats every 2 pi units. But the sine of 1 over x, it also goes between heights -1 and +1, but as x gets closer and closer to 0, the function oscillates very, very quickly. So you might have some kind of wave going on here, and then as x gets closer and closer to 0, you just get this wave pattern that oscillates so much on either side of 0 that, and this continues, then the wave continues on either side. So what's happened is the function is oscillating an infinite number of times as x gets really, really close to 0. So if we looked at the limit of f of x as x approaches 0, again we would have to say that this limit does not exist. So the reason why it has no limit is because it just oscillates too much. As x gets closer and closer to 0, the function oscillates too much to have a limit. So the values of sine of 1 over x are not getting closer and closer to one particular number as x gets closer and closer to 0. So these are some examples of how we can compute the limit of a function. In future lessons, we will learn more techniques for evaluating limits using limit laws and using algebra.